Okay, let's jump right into this. Welcome to today's Explainer, where we're going to tackle a massive, honestly, pretty invisible challenge in modern science. We are talking about bridging the huge gap between rigorous academic citation standards and the chaotic, messy reality of actual software implementation.
We're kicking things off with this incredibly relatable quote from Marcel Ballman just to highlight the exhausting friction researchers are dealing with when they try to programmatically format citations. I mean, you'd probably think that with Python's massive ecosystem, generating a bibliography straight from code would be a total breeze, right? Well, the reality is that research software engineers are basically pulling their hair out and losing their weekends, trying to get these wildly disparate systems to just talk to each other.
So here's our roadmap for today's Explainer. We'll start by looking at the Python citation nightmare. Then we'll move into retrieving raw metadata, filtering that data programmatically, generating camera-ready BibTeX, and finally, we'll wrap up with traceability and persistent identifiers. Let's get into it.
Part 1. The Python citation nightmare, stitching together broken tools.
Now, in a perfect world, the ideal state is a seamless data pipeline, right? Clean data goes in, you do some programmatic filtering, and boom, perfect formatting comes out. But the Frankenstein reality we actually live in, developers are desperately patching together complicated, dead, totally unmaintained Python parsing libraries with legacy formatting engines. And they're holding the whole shebang together with super fragile regex code.
And this dysfunction is happening at a huge scale. Standard tools are actually literally dropping vital data. Take CyprocPy, for example. It silently discards absolute must-have fields like URL and DOI. Even crazier, parsing will outright fail if author names happen to be separated by 2 spaces instead of 1. No way, right? Plus, because traditional formatting engines are rooted in print media, they strip away all the semantic markup. They just spit out direct visual styling, like italics or bold, instead of nice, clean HTML tags, which means developers are forced into these really risky, error-prone regex search and replace operations just to highlight a specific author's name.
Moving on to Part 2, retrieving the raw metadata, a clean break from the chaos.
So, how do we escape all that chaos? Well, we replace that Frankenstein setup with a clean 3-step programmatic pipeline. We're going to do a visual step-by-step walkthrough right now to track exactly how we retrieve raw metadata, filter it programmatically, and finally export camera-ready BibTeX.
Look at this. It all starts right here, with just one brilliantly clean line of code, calling academiccitations.getCitation for Pontryagin 1962. We instantly request the exact metadata for a specific mathematical model. This little citation object becomes the hero of our pipeline, smoothly pulling exactly what we need without any of the usual fuss. Boom! Instead of losing fields to those buggy, outdated parsers we talked about, our object successfully yanks all this incredibly rich, totally intact metadata directly from the database right into our code execution. We get the authors, the year, the title, the mathematical theory of optimal processes, and even custom fields, like how it specifically relates to Studio OS scheduling.
All right, Part 3. Filtering the data programmatically. Precision without rejects. Because we successfully retrieved a clean object, we can now filter and interact with it totally programmatically. By calling its attributes directly, like sit.authors or sit.year, you maintain complete 100% programmatic control. You're completely bypassing the need for messy regex text replacements and entirely avoiding that lack of semantic markup that usually ruins traditional HTML pipeline outputs.
This is an absolutely massive leap forward, and here is the so what of why it matters so much. You see, scientific software isn't just arbitrary code. It encodes really rigorous domain knowledge and assumptions that absolutely must be handled with exact precision. By preserving complete data structures, we dodge fragile rejexes, and more importantly, we can seamlessly embed these complex academic assumptions directly into our core code logic.
Part 4. Generating camera-ready BibTeX, the final export.
And here is the magic. With literally one final command, the pipeline effortlessly translates all our filtered, precise metadata into a fully standardized BibTeX format.
This is what we call camera-ready BibTeX. It's the ultimate relief to our earlier nightmare, giving you flawlessly formatted references instantly. We're talking 0 manual post-processing needed to meet those incredibly strict standards of academic publishing. None!
And let me tell you, this automated formatting is an absolute necessity, because different journals have incredibly unforgiving citation rules. For instance, APA 7 demands a strict bracketed label for computer software. Meanwhile, IEEE requires exact numbered formats. Imagine managing that manually at scale for hundreds of references. It's a guaranteed way to introduce errors. Programmatic generation of these formats is, for sure, a total game changer.
Finally, Part 5, Traceability and Persistent Identifiers, zooming out to the ecosystem. Look, if you're writing academic software and you actually want others to cite your work properly, which, let's be honest, is absolutely critical for your career and funding, you must follow these best practices. You need to guarantee that your exact software version is persistently discoverable. The best way to do this, integrate your GitHub repository directly with Zenodo. By including a citation.cff file, every single time you create a new GitHub release, it automatically triggers a Zenodo snapshot. That gives you a persistent DOI that you can just pin right in your README.
Now you've got to understand the distinction between DOIs here. Cross-ref DOIs are fantastic for formal, peer-reviewed publications like journals. But Zenodo DOIs, they offer the flexibility you need for the messy, day-to-day reality of software releases. By utilizing Zenodo, you ensure your exact code versions never fall victim to a deleted repository, renamed files, or force-pushed URLs. It creates a truly auditable, permanent record.
And that permanence is absolutely vital. As this quote from Fortune Sensum Julish reminds us, scientific software encodes assumptions. Its outputs literally become scientific evidence. Even as agentic AI accelerates coding and automates all these engineering layers, the scientific judgment, the validation workflows, and the strict traceability of these embedded methods, that remains entirely our human responsibility.
Which brings us to our final big takeaway for you to ponder today. If your software executes a scientific theory, can your code genuinely trace it back to the source? True scientific reproducibility means your codebase has to transparently, reliably, and programmatically cite the theories it executes. By properly bridging this gap between code and citation, we don't just write better software, we build a much more trustworthy foundation for all future science. Something to think about.